Hello everyone, I'm Vivek Baskar. Today myself and Harikrushna will be presenting the paper on two-dimensional fair queuing for multi-tenant cloud services. The authors of the paper are Jonathan, Peter, Madanlal, Rodrigo, and Krishnan. So this paper was originally presented in Brown University with partnership of Microsoft. Before we deep dive into the paper, first we will understand what is multi-tenancy. So here is the comparison of single tenant versus multi-tenants. In a single tenant setup, the applications or client will be deployed to a single server or VM, and it is connected to its own database. In the setup, none of the infrastructure is shared between the tenants, and each of them would have their own servers and VMs connected to their databases. Whereas in multi-tenant setup, multiple clients or tenants will use the same infrastructure. The resources such as VMs, servers, databases would be shared across the tenants. And of course, there will be logical separation of resources, which will provide the service isolation between the tenants, but the tenants would share the same resources where they would run the code. This page provides a detailed outline of the infrastructure setup for single tenant and multi-tenant. Here on the right hand side, we can see the single tenant setup. So where we have our host hardware, and top of it we have the hypervisor, which enables us to run VMs, and on top of it we have different VMs, which is handled and maintained by a single tenant. So the client, a single tenant, would own or would run all the applications of theirs in this particular setup. Whereas on the left hand side, we have a concept of multi tenancy where we have the host hardware hypervisor and VMs on top of it. And here the difference would be the VMs, the respective VMs would be handled or maintained by multiple tenants rather than a single tenant. So this multiple tenant concept is supported by most of the cloud providers today. The examples are GCP, Google Cloud Provider, Azure, and AWS. So queuing comes into picture in case of multi-threaded or multi-tenant infrastructure, where each tenant has its own queue, which is executed on a shared VM. So the process execution depends on the algorithm and the queuing technique used on the process. So most common algorithms would be specific to request processing and request switching, where the each request from the tenant queue would be taken and would be placed in the process to be executed depending upon the queuing techniques and the algorithms used. So this um, drastically varies the performance of each of the tenants and how it is being processed on the shared process. So there are various queuing techniques which exist in different scenarios. So the most common one and the queuing techniques which are mentioned in the paper are weighted fair queuing, start fair queuing, worst case fair weighted fair queuing, and two-dimensional fair queuing. So in this paper, The last one, the two-dimensional fair queuing, is proposed, which overcomes the disadvantage or shortcomings of the queuing techniques which is mentioned above. We saw various queuing techniques. So now we will see the 2D fair queuing technique. So many cloud services only implement first in first out queues, which causes denial of service, which occur in Hadoop, OpenStack, and etc. Basically, the worker threads invoke fair queue scheduler to decide which request should be dequeued and placed on the process. So this gives application control over the choosing the request precisely and get to um avoid running into context switching overheads and efficiently supporting requests that might only be in tens of microseconds in duration. 2DFQ proposed in this paper provides fair and smooth schedules to the request in the queues by minimizing the burstiness over space and over time. So these are the advantages of using 2D fair queuing. And this is achieved in two-phased approach. In phase one, schedulers separate the request based on size, cost of execution of different requests. Then the request can be placed on a separate thread, which will substantially reduce the burstiness. The non-blocking large requests are then placed on a different thread, which won't affect the other short-lived request on the different thread. In phase 2, cost determination based on request size and time of execution is calculated. For the unknown request cost, pessimistic cost estimation technique is used. And also collocate unpredictable requests together. So the primary motivation of 2DFQ is to improve existing fair schedulers to avoid bursty schedules, to handle unknown cost, fine-grained resource isolation for the request, to avoid service denial for tenants, to achieve fair scheduling. So there are various challenges which occurs in the shared process, especially in a multi-tenant setup. So few of the challenges are listed here. Resource concurrency, large cost variance, unknown and unpredictable resource cost, bursty schedules, high latency. So the high request cost variability can be seen in this picture shown here. So we have APIs from A to K with their respective cost. So the request cost varies up to 4 orders of magnitude. So the API cost estimates depicts that A is cheap and G API call is being expensive. On the other hand, the other graph shows the variation for the different tenants from T1 to T12. So all these APIs and the tenant cost distribution is carried out in Windows Azure platform. Now let's see how two-dimensional fair queuing algorithm works if cost is known for the request. So 2D extends worst case fair weighted fair queuing technique. So it chooses the request with the lowest finish time, and also uses eligibility time to place the request in the process. And one other technique which is used is to determine the future step by looking ahead of time of the request. So below is the formula used to place a request in the process. So this provides the eligibility of a request. So if the thread is eligible, if the request is eligible, and it will be processed in the put in the process for the execution. So the picture here represents the implementation details of NQ and the refresh algorithm. So when the cost of the request are unknown, then 2D uses pessimistic cost estimation technique as seen before. So it assumes the requests are always expensive. So this helps in predicting the cost for unpredictable request. This is very good for smaller tenants, where the smaller tenants doesn't have to wait in the queue for longer, being blocked by the uh, larger queues. And also from statistics, it is proven, or it is shown that there is a very small percentage of requests that are unpredictable. So here on the picture, it depicts the implementation of the DQ and the complete algorithm for 2D FQ. So these four algorithms put together forms the 2D fair queuing algorithms. So with this, I believe we would have got a fair idea of two-dimensional fair queuing algorithm, its advantages, and also the implementation details of 2D FQ. Now I'll hand over to Harikrishna to discuss on rest of the topics.
Thank you, Vivek. We will now move on to the evolution. Authors implemented 2DFQ as well as several other algorithms. But for clarity and due to similarity and results, author present results comparing 2DFQ only to weighted fair queuing and worst case fair weighted queuing. Authors evaluated 2DFQ in discrete event simulation using production workloads from Azure Storage. In the presentation, I am going to focus on showing how 2DFQ produces smooth service, first with known costs, then with unknown costs. But in the paper, authors present numerous experiments exploring other dimensions and evaluating the effects on bustiness, fairness, and in particular, tail latency. So in the first experiment, we will examine 2DFQ for synthetic workload with known costs. We have 50 small tenants like tenant A, all submitting requests with a size of approximately one sample from a normal distribution, and we have a 50 large tenants like C with cost approximately 1,000, also samples from a normal distribution. The tenants share a server with 16 threads where each thread can process 1,000 requests per second. Running these workloads, let's look at the throughput or service rate over time for one of the small tenants. For worst case weighted fair queuing, we can see that the service oscillates over the time. For worst case fair weighted fair queuing, we get much more start behavior. This service is really bursty period of high throughput followed by nothing. To illustrate why this is the case, we can visualize the request that each thread is running at point in time. The lens in the figure represents threads. Dark shading indicates the thread is executing a large request, and light shading indicates a small request. We can see that work in fair-weighted fair queuing is oscillating between periods of only large and only small requests. Finally, in 2DFQ achieves much smoother service for this tenant. Again, looking at the thread occupancy, we can see that for 2DFQ, requests are partitioned across threads based on size quite effectively, which explains the smoother servant service. So here is another example. So we will look at the similar result, but this time for real workloads from Azure Storage using workload samples from 50 production machines. Authors randomly select 250 tenants and replay their request on 32 threads, each with capacity of 1 million units per second. In addition, we are going to add in the workloads of these 12 tenants that we looked at earlier in order to evaluate burstiness. We are going to examine the service received by tenant T1, since T1 is a representative of small tenant with small requests that are most affected by burstiness. WF2Q actually does pretty well with only a few spikes of burstiness. In the upper part of the slide, we have shades for threads based on the size of request that is executing at a point in time, with darker meaning more expensive request. For WF2, for WF2Q, we can observe how the spikes and service down here correspond to multiple large requests occupying threads simultaneously. On the other hand, 2DFQ smooths those spikes out too and produces even less bursty service as before. We can look at the thread occupancy over time across all tenants. In 2DFQ, we can see that requests are successfully partitioned across threads based on size with large requests on lower index threads. Now let's expand on this example and look at one final experiment to see how things deteriorate when costs are not actually known upfront. With the reference to this figure we saw earlier, we are going to run three types of workloads. So here are the three types of workload. The first workload will relatively predictable with 300 tenants and the same setup as the last experiment. The second workload will replace one third of tenants with ones whose requests are deliberately variable in cost and difficult to predict. And the third workload will replace two-thirds of these tenants with deliberately unpredictable ones. This means that across the experiments, the service is expected to deteriorate and become busty. So this is the workload for WFQ. So let's look again at T1 throughput. As the workloads become less predictable, weighted fair queuing gives bustier and bustier service. This is the workload for WF2Q. Similarly, WF2Q does reasonably well when the workload is predictable but also deteriorates as the workload becomes less predictable. And this is the workload for 2DFQ. 2DFQ does very well when the workload is predictable and also deteriorates as the workload becomes less predictable, but by nowhere near as much. So this is all three together. We can finally observe how 2DFQ scheduled its unpredictable tenants. To summarize with 2DFQ, we can take advantage of the fact that we have multiple threads which enables us to reduce bustiness for tenants that have smaller requests. We do this by partitioning requests across thread by size and by co-locating unpredictable and expensive workloads. The results the result is that as workload becomes less predictable and the range of request cost increase, 2DFQ gives good quality of service where other two algorithms rapidly deteriorate. As a result, 2DFQ reduces burstiness and significantly improves tail latency. So we have find some issue for this paper. So this paper assumed that there is no dependency or communication between threads and each request is like an atomic unit, but there is no solid evidence provided in this paper. So if threads are accessing the same data, then there could be a conflicts between those threads. So in future, we can additionally consider the dependency between different threads. And here are some improvements we can take. So the goal of this paper is to produce smooth schedule without long backlog time by reducing bursty condition. So the one way to improve this property is to separate predictable and unpredictable requests into different threads. By doing so, we can ensure that predictable requests will not affected by unpredictable requests. This will prevent requests with constant growing size to have influence on those requests with predictable size. With that said, we conclude our presentation. Thank you.